So let's have a look at inequations and solving them. Basically, it's exactly the same as an equation, really. All the techniques that we use. The only difference is instead of an equal sign, we have an inequality sign. Might be less than, might be greater than, less than equal to, greater than equal to, one of those signs. There is a difference though. A couple of key things to remember when you're solving this, unlike in an equation. If you multiply or divide by a negative number, then you've got to change the inequality sign. Now the way I always remember that is if you change the sign, you change the sign. So if you change the sign of the number, you change the inequality sign that's between them as well. So if you change the sign, you change the sign. The other one, which a lot of people forget about, it doesn't come up that often, but reciprocals. If you take the reciprocal of both sides, then the inequality sign's got to change. Because if you think about it, 3 is greater than 2. But if you turn those upside down, 1/3 is not greater than a half, it's less than a half. So if you were to turn both sides upside down, that's the other situation. It's a lot rarer, but it's something we should keep in mind. All right, start with very basic ones and then we'll build our way up to some more interesting inequations. 6x is less than 36. So I say, just like an equation, I'll divide both sides by 6. Voila! Not an incredibly shocking one there, but I use this as an illustration of how we plot these things on a number line. So I usually, obviously the point I'm interested in is key. So make sure I plot 6. If it's just one number, I tend to put the one either side just to give it a bit of scale. It's not included, so we circle the point to indicate the boundary is not included. And then we draw an arrow to indicate which direction, and basically the arrow matches the inequality sign. So less than, so we're going to the left. Now, I know there are some teachers who are obsessed with, oh no, you've got to put that line on the number line. And you'll notice I haven't, and I never do, right? Because depending on what type of pen you're using, you can lose the arrow on the number line. So I always just put it a little bit above. The difference between an inequation and an equation is you can actually have 3 sides. I mean, equations, of course, only have 2 sides. And then normally we say what we do to one side of the equation, we do to the other. So when it comes to an inequation, we say, well, what we do to one thing, we do to everything. So for this one, I'll take 6 away from everything. Now we'll divide by -4, but if you change the sign, you change the sign. And hopefully right now you're looking at this and you're starting to get sweaty and cold and go, hang on, because you're looking at that, and it just doesn't, no, let's rewrite it, thank you, oh, phew, now we feel much better, okay, because that second last line is horrible, it just looks terrible. If we were to plot that, then in this case, I probably just put the 2 points I'm interested in. This time we colour in the circles, because the boundary is included, and I want in between the 2 points. In between the 2 points. So anyway, that brings me up to the Mr. Simmons is very fussy, correct way of writing inequalities. You'll notice correct in inverted commas, correct, because Mr. Simmons is very fussy. Okay. I think the algebraic solution and the geometric solution should match. They should look like each other. That's my opinion. So something like that would be x is greater than 5. Look, it's the arrows going in the same direction as it looks nice. It looks beautiful. Okay, no, don't write 5 as less than x. Think about how you say it. The question is asking you to find all the possible values of x. So you're answering it and saying, oh, you want all the possible values of x? Oh, x can be bigger than 5, right? But if you were to answer 5 is less than x, I go, well, that's terrific. 5 is less than x, but what else do you know about x? You're not telling me about x, you're telling me about the number 5. Fussy. Okay, something like this one. So we're in between. So I would write it like that. Again, it looks like the picture. X is in between the 2 numbers. So 4 is less than x is less than or equal to 6. As I just mentioned, no, that doesn't look like. When do you see 6 before 4, other than in the number 64? No, don't start listing every number. Okay. And, oh, no. Don't write that. x is greater than 4 or x is less than 2, because that one's just plain wrong, because it's not or, it would actually be and. If you were, for some insane reason, if you did want to write that as two inequalities, you have to use the word and there, not the word or. But don't do it that way. Make it look like the picture. Okay, then we have these ones where they're on the outside of the solution. So again, look, it looks like the picture. X is less than or equal to 4 or x is greater than or equal to 6. No, again, all right, I'll concede. I can't make you wrong if you put that, but I'll be marking it with a tick through gritted teeth. All right. Again, 6 before the 4. Where does 6 come before 4? And no, we don't write it that way. That just looks weird and is actually wrong. All right. So as I say, there you go. The Mr. Simmons very fussy way of writing in equations. Let's solve a quadratic one then. So we looked at the linear ones just before. Now let's look at quadratics. So something like this. Well, the key to a quadratic is to find the two solutions if it was an equation. So let's do that. I'll factorise, same as normal. I now know the solutions are -6 and 1. That's where I draw up a picture. Now you could use a number line if you wish. I'm using a number plane. So we know 6 and 1, well, they're not included. If I was to draw that, I know I'm getting a parabola and it's concave up. It doesn't matter what the vertex is. I'm not interested in that for this problem. So I just need a rough sketch. And so now I can look at this parabola and go, well, hang on a sec. What values of x is the y value less than 0? That's essentially what that's saying. So I can look at the picture and go, oh, look, the y values are below 0 in between the two numbers. But of course, I'm only interested in the x values. So there it is. There's my solution as a picture. I can then write down -6 is less than x is less than 1. Now, let's say some people use a number line rather than a number plane. Similar idea, if you use the number line, you'd plot the 2 points and then you would just test numbers in the regions to see which one that works for. Let's do another one. I hate -x squared. I'll say it right now. I hate it, okay? So I don't know, there's something about it when I try and factorise it with a -x squared. Something just doesn't work for me. So I change it. But of course, if you change the sign,
you change the sign.
So let's factorise it. We get x plus 4, x minus 1. This time the 2 points are included. Because I always make mine x squared, I always end up with a concave up parabola. And this time though, I'm saying, when is this parabola greater than or equal to 0? For this one, there and there. So there's my solution. Quadratic inequalities, because we're talking about a parabola, and we're always going to be asking this question, when's it below, when's it above? The solution will always end up with x is in between the 2 points, or is on the outside of the 2 points. And so that's why I say some people prefer to just use the number line, because they know the solution's either going to be in between or on the outside. They just pick a point to test to see which region it's in. But basically, to solve any inequation, really, you can do that. Solve it like an equation and test the regions then between the boundary points. Let's have a look at absolute value inequations then. So something like this. Now, you may recall when we looked at the equations, I said, if we think of it like the definition, that'll make these ones easier. So I think of it like the definition, and I know if it's the absolute value of x plus 5, either it's positive x plus 5 is less than 2, or the negative of x plus 5 is less than 2. If you were to go plus or minus 2, you're going to have problems with the inequality signs. So that's why you always do it via the definition, and you should never have a problem. Solving the first one, x is less than -3. The second one comes up with x is greater than -7. I personally like to draw up a graph to make sure, is this an intersection or are we on the outside? So -3 goes that way. Okay, so we must have the intersection in this case. We're in between the 2 points. But once again, you could just test a region and see where you are. So -7 is less than x is less than -3. Let's do another one. So same idea, either 3x plus 2 is greater than or equal to 1, or the negative of 3x plus 2 is greater than or equal to 1. Solve the first one, I get greater than or equal to minus a third. Second one, less than or equal to negative 1. Let's have a look at those. So minus a third. Okay, so this time it's not the intersection, it must be the union of the two solutions. So we've got x is less than or equal to negative 1, or greater than or equal to minus a third. An alternative method, you can turn an absolute value equation into a quadratic inequation. Absolute value of x plus 5 is less than 2. Square both sides, because you know squares are always positive, just like the absolute value sign. So it becomes x plus 5 squared is less than 4. And now you solve it like that quadratic. So we end up with, factorising it back down once we move everything over. Surprise, surprise, there's our answers, x plus 7, x plus 3, giving us the two possibilities of negative 3 and negative 7. And bang, you got the answer. Let's try the second one. It's the same idea. Well, I'll square both sides. And what do you know? I've ended up with the same critical points, we call them. And so x is less than or equal to negative 1. Or greater than or equal to minus a third. Next type, ones where you have pronumerals in the denominator. So I'll start with a very simple one, our hyperbola. 1 over x is greater than or equal to 3. Now I've got to admit to you, I probably know about 5 different ways of solving this problem, and it's probably because I've marked this in the HSC in the past, and so you see every method that you can possibly think of. So 1 over x is less than or equal to 3. I'm going to show you what's the most successful method. There are two commonly used methods, so commonly used ones. One is the most commonly used, but the other one is actually the most successful method. You get least mistakes in it, and that's the one I'm going to show you. First of all, what's causing us the problem? The problem is the bottom of the fraction. So let's find where the denominator is 0. Well, in this case, that's just x is 0. So I know x can't equal 0. Now I just solve it like it's an equation rather than an inequation. So 1 over x is equal to 3, x is a third. Okay, and then I just use my number line. Plot the 2 points. Now, a third is included because it's greater than or equal to. But 0 is not included because bottom of the fraction can't equal 0. I've just got to pick a point. If I picked negative 1, I'll get 1 on negative 1 is greater than or equal to 3. True or false? No, that's not true. All right, let's test one in the middle. That's a little bit harder, finding a number between 0 and a third. A quarter. 1 on a quarter is greater than or equal to 3. That's certainly true. So yes, I know I'm in the middle. Well, I did the one before, but let's do it again. There it is. X equals 1, and we'd already determined that actually that one's false. And so there's my solution. 0 is less than x is less than or equal to a third. Okay, that is the most successful way of solving this. It's what's called the critical points method. You find those critical points. What are the boundaries? And once you know the boundaries, you just test either side of the boundaries to see where it actually exists. Let's do it this way first though. So 2 on x plus 3. So what's causing me the problem? Bottom of the fraction. I know x can't equal negative 3. Now solve it like an equation, and I get x is negative 13 on 5. Plot that on the number line. In this case, both of those boundary points are not included. Test a point. Well, 0 is easy to test, isn't it? 2/3 is less than 5. True or false? Okay, so 0 must be included. And so I end up there. Because interesting thing is, with these linear ones in the denominator, it's just like a quadratic in that it's either going to be in between or on the outside. But if you're unsure, test all the regions. Now, back to this one, what you wanted to do. This is probably the most commonly used one. Here's the idea. So again, we turn it into a quadratic equation. 1 on x is greater than or equal to 3. Multiply both sides by the denominator squared. The reason we do that is because now I know I'm multiplying by a positive number, and therefore the sign won't change. So we couldn't do it before that. If I was to just multiply by the x, I don't know. Is x positive or negative? So does the sign change or not? I don't know. So that's why I've got to multiply by x squared. So I know I'm multiplying by a positive number. So we end up with x is greater than or equal to 3x squared. Move that over, we get 3x squared minus x. There's our quadratic. Solve it. And surprise, surprise, We get the same numbers, 0 and a third, x's in between. Take care of the domain issue though, because notice my answer. And this is the problem, and this is why it's not as successful. Because people do this and they go, oh, there's my answer. But they haven't thought about the bottom of the fraction can't equal 0. And so they've just solved it. They've turned it into a quadratic, solved the quadratic. That is the correct answer for the quadratic. Remember how I was saying, was it yesterday or the day before? That sometimes when we solve things, we change the question something easier to work with, and we come up with the solutions, but we might come up with extra solutions. This is a situation like that. We've come up with an extra solution of x equals 0. So you always go back to the original question and make sure your solution works. Bottom of the fraction can't equal 0. So that's no good. In other words, it's just x is in between 0 and a third, but not including the 0. So you do need to be careful when you're using that method. Let's do our second example that way. So this time I'll multiply by x plus 3 squared, or move across. Don't expand out. That's wasting time. Because they've got a common factor of x plus 3. Think about what you're about to do. You're about to factorise the quadratic. It's already partly factorised for you. Take advantage of that. So just move everything to one side and go, oh look, it's got a common factor of x plus 3. So it's x plus 3, 5x plus 13 in the other factor. And we get our same solution as before, because that one's fine. Check the original one, bottom of the fraction. Well, no, I haven't included -3 for this, so everything's okay. All right, 5a is on inequations.